Hey there, physicists. This is Mr. Clegg. We're going to talk about kinematics equations, constant acceleration equations. Kinematics means the study of motion. And so we're going to work with this today. First of all, if we have a situation with constant acceleration, it means that the velocity is changing at a constant rate. We have a few quantities I want to talk about first, and then I'll show you the equations and how to use them in a problem. Okay, so x minus x naught is the displacement. And by the way, this naught thing is just zero, but in England and other countries, they use the word naught, N-A-U-G-H-T, instead of zero. So just by tradition, I guess we call it that. So v0 is just or v naught is the initial velocity, the velocity at time zero, time zero. So anyway, so we have x minus x naught, that's the displacement, initial position, right? And then we have the position now. The difference between those is the displacement. We could also call that delta x, right? Final minus initial position, which would be the displacement. A is the acceleration. V is the present or the final velocity. And then V naught is the initial velocity. T is the time. So those are the five quantities. And the secret to solving these constant acceleration problems is if you know any three of those, x minus x naught or delta x, you can treat it as one thing. It's how far we went in displacement, right? So if you know any three of these five, you can solve for the other two. And now I'm going to show you the equations that we use to do that. These equations are only valid when the acceleration is constant. So I'm just going to show you really quick here. The acceleration, of course, is the change of velocity over time, right? So it's the change of velocity over time. That's the definition of it. But if you rearrange that, it ends up making this equation. So that's just the first equation. Now, for any acceleration, whether it's constant or not, this would be the average acceleration. But if the acceleration is a constant, then the average is the same thing as the acceleration. So that's what that becomes. All right. Now, I think I'm going to erase this just so my thing doesn't get too cluttered. Whoops. Try this. All right. Now, back to this. We have another equation here. I think these might be derived in the book somewhere, but personally, I don't think deriving is super important for me to put you through, how you combine this equation with another one, and then you get it to end up being the this next equation. So this one we have x minus x naught or delta x. X minus x naught is equal to v naught t plus 1/2 at squared. All right. All right. So that's another one. It relates all of these equations. This one relates four of these five quantities. And we'll get to that in a minute, exactly how we make sense of all that. The third one is v naught squared, sorry, v squared equals v naught squared plus 2a delta x, or x minus x naught, right? So those are the three that oftentimes are given in books, but there are two more that are pretty nice. I'll just quickly derive one of these for you. So as long as we have constant acceleration, remember these equations are only good when the acceleration is constant. If we have constant acceleration, that means we have a straight line velocity graph. So let's just say our velocity starts at some value here and goes in a straight line and ends up in some later value. Time goes from 0 to t, right? So otherwise we'd say t2 minus t1 or t minus t naught or something like that. But we're going to say we start at time 0, right? So if we go from v naught to v in a straight line, that means that if we wanted to find out the average, right? If we wanted to find out the average speed, if it's a straight line, it would just be the midpoint, right? It would just be the midpoint of this line, right? So there's our average, right? Here's our average speed, right? I'm gonna erase that so it doesn't get too messy, but the midpoint of that line is our average speed. So in order to take the average, right, we would just go like this. 1/2 of the initial plus final velocity, right? That's a little messy, so let's try that again. Okay. There we go. So that's our average velocity. But if we wanted to find out the displacement, right? So we could go like x minus x naught is equal to the v average times the time, right? So v average is the displacement over the time. So we just pulled the time to the other side. And so we can actually just replace this guy in there. And so we end up with x minus x naught equals, it's just going to be 1/2 v naught plus v times the time. So that I just quickly derived that fourth equation. This is one that is very useful, I find. So here we have this. All right, so x minus x naught equals 1/2 v naught plus v times t. And I'm sorry that there's so many equations in this. Most units in physics, you only have one or two important equations. This one, we end up with a bunch, but they're all very useful, and you can pick one for whichever thing that you need to do. The final equation is almost the same thing as the second equation. It's almost the same as this, but we're going to change this to a minus sign, and we're going to change this to v instead of v naught. That's the only changes. So it's going to be x minus x naught equals vt instead of v naught t, vt minus, instead of plus, 1/2 at squared. So that one is in some ways kind of easy to remember. If you can know this one, you just v naught becomes v, that becomes a minus. Now, each of these has 4 of the 5. So the reason why I decided to use all 5 is because it makes problem solving actually a lot easier when you're doing kinematics problems. So you might notice, like, which of the, this one has v naught, it has v, right? This first one. It has a and it has t. It doesn't have, so I'm gonna make a special note here of what it does not have. Doesn't have x minus x naught. Doesn't have the displacement, that first one, right? This second equation, if you take a look at what it has, there's the displacement, there's the acceleration, there's v naught, there's t. It doesn't have v, right? So it doesn't have the final or current velocity. This one doesn't have v. This one doesn't have t. This one doesn't have the acceleration in it. And this one doesn't have the initial velocity. So now you have an equation for, as long as we have constant acceleration. If we don't have constant acceleration, we can't use any of this. So we can only use it if we have constant acceleration. But that's a lot of situations. So I'm going to demonstrate how to use these. And in order to do that, I'm going to go ahead. Actually, you know what? I'm going to do a separate video just so this video doesn't get too long. I'll start a new video in a moment, and then we'll practice how to use these equations in a problem. Okay, see you in the next one.